Hello everyone and welcome to another Stat 437 lecture video. In today's video we are going to be talking about fitting continuous time regression models using the Survreg function in R. So it's from the survival package. And in particular, what this is it's a package that sort of fits the location scale models that we were talking about in the last lecture. So what we'll do today is sort of read in some data. I have that posted on the course website alongside the code that we're going to be working through. And we will just fit some basic regression models without actually specifying any covariates. We're just going to essentially use the parametric form that we were talking about last time and sort of see how we can use R to get the fits from that. But this leads us directly into the next topic and sort of the first of the major classes of models that are commonly used for continuous time survival data, which are the accelerated failure time models. Okay, so we'll see in R today, we'll sort of stop short of using any covariates or fitting sort of more complex models. But then in the next lecture, we're going to introduce formally how do people think about these types of regression models. Okay, so as always, everything that we're going over today should be posted to the course website. If you have any questions, please reach out and ask me. And otherwise, we can get started. So I have my R open over here. And the first thing that I want to do is just talk about the survival library very quickly. So again, I will just load this in. You will want to make sure that you've installed survival otherwise, and it just gives you some tools for dealing with survival analysis. The other thing that I want to do is actually just read in some data. And so I'm going to read in this customer churn data. This data set's posted to the course website. And the idea with this data set is that it's supposed to represent data from a telecommunications company, and it's how often their customers are churning. And what we mean by that is, at the end of any given billing period, some number of customers are going to cancel their accounts, right? And the idea here is that we're going to try to use survival analysis to model the time until a customer cancels their account, right? And so that would be the event of interest is account cancellation. And then because we only have a window of data, everyone else who did not cancel during that time period is censored, right? So the other thing that I want to do is I just want to redefine the event. So in the data set, we have this column called censored, right? And so it's a censoring indicator. And I just want to also include an event indicator. So I'm going to define churn event to be 1 minus churn censored. And that's going to give us sort of that event indicator as well. If I just view this data quickly here, you can see that we have quite a few columns. It appears to be 22 now, right? But for the most part, this should be fairly self-explanatory. So we have the individual ID. Each person gets one row in the data. We have the time period and whether they were censored or not, right? So censoring of 1 means that the event was never observed. We have the total charges over the lifetime of their account, as well as the monthly charges presently on their account. So I should note that time is being measured in months, and while that's a discrete value, you can see that, if we sort it, a number of people only have 1 month, and if we flip it up, it goes all the way up to 72, right? And so treating that as a discrete time value is probably not super wise on account of that sort of is going to be too many categories to treat discretely, right? But yeah, so we'll treat this as continuous. And then we have information about the contract that they're on, what their demographic information, what services they pay for, and so on. And so there's a lot here. All of this is really well documented on the course website, what all of those columns are. And we'll play around with this data a little bit today, but also in the next lecture once we see accelerated failure time models. We'll come back to this data set in a little bit more detail, but I'd also encourage you to play around with it. I think that this is like a very interesting problem to work on survival analysis with. It's outside of the biostatistics literature, of course, which might be interesting for some of you who aren't looking to go forward with biostats, but it's sort of a real life example of the types of ways that this survival analysis could be used. Okay, so the first thing that I want to do is actually just begin talking a little bit about this survival package, okay? And so the first call that I'm going to introduce is this call to this serve function. And so I'm going to define a variable here. I'm going to call it survival object. and I'm going to call serve. And what serve is doing is it creates what this survival package deems a survival object. And so what we need to do is give it a time variable, and then we need to give it an event indicating variable. Okay. And so if I just run that, you can see that we've created this survival object here. And the idea is that this serve function is taking care of whether or not the individual, this time that's being observed is an event time or whether it's a censoring time. So it's sort of defining behind the scenes those delta indicators that we've been talking about, and then using those to fit the models parametrically without us needing to actually go in and worry about specifying those. So this call to serve is going to handle sort of all of that for us. Now, one thing that's nice is once we have this survival object, we can actually sort of get plots of it. And so I'll make sure I extend all of this here, but then I can just call plot on survival object. And maybe I'll just give it an X label of months just to clarify this. But what we have here is sort of this estimated survival curve here, and it's a non-parametric estimated survival curve. It's a topic that we probably won't get to talking about in class this term, but the idea is that essentially this is the observed rates of survival in the population, and then we have sort of a confidence band on it, right? And so you can see that within month 1, there's quite a large drop off, right? But then after that, we have this nice sort of smooth curve going on. And so we're going to actually sort of exploit that structure later on. But this is one of the nice things about the survival object here, is that once we have it created, it sort of can be manipulated directly as a survival object. Now, the main function that we're going to be interested in is called Survreg. And so it's in the survival package, and it's Survreg for survival regression. And if I just pull up in the documentation here, Survreg is going to be quite familiar to us at this point. It's going to be quite similar to the other regression style formulas that we have in R. And so essentially, we're going to provide it a formula which specifies some sort of regression model. And we'll see these in the future, but it sort of looks like the linear modeling that we're used to. We provided a data. And then the other piece that we want to specify is this distribution, right? And so you can see that we have the Weibull, exponential, Gaussian, logistic, log normal, log logistic. These are all distributions that we were talking about in the last lecture that are common for survival data. And then essentially what this is going to do is it's going to parametrically fit those models that we were talking about. All right, so the documentation's all there. You can give it a look if you need to. But for now, what I want to do is actually just fit our first model. Right, so let's say that we assume that the exponential distribution is a fair distribution for this. And again, we're not going to actually use any covariates to explain right now. We just want to get a maximum likelihood estimate for that parameter of interest. So the outcome of a Survreg is going to be a serve object. And so we'll say it's the time and the event. And I just want to fit it using an intercept here. We pass in the data, which is in our churn data set here. And we want to specify the distribution, so dist, and we can just specify that to be exponential. Okay, so that's just an error relating to my graphics. That's fine. We have this model object here, and just like most model objects that we have in R, we can take a look at the summary of it. And if we do a summary of model 1, you can see that we have this fitted model. We have an estimated intercept term here, and here what we're saying is that the scale is fixed at 1, and that's because if you remember, the exponential distribution is only a 1 parameter distribution. The other parameter, it's fixed to be 1, right? So when we were looking at it from the Weibull distribution, you get an exponential by holding the scale fixed at 1. Okay, so that's essentially the idea here, is that we've fixed the 1 parameter and we get a maximum likelihood estimate of the other parameter. Now, if you remember back from when we were looking at the table, in the exponential distribution, we actually sort of saw that it was log rho plus W. And so what that means is that our coefficients have to do with this log rho. And in particular, we've estimated 4.8039 is equal to the log of rho, which means that, of course, we can get rho as the exponential of that value, right? And so if we wanted to start doing inference on the exponential distribution directly, we could use this exponential transformation, right? So how might we actually go about doing that here? Well, the first thing that we might be interested in is getting a hazard estimate, right? So we had said in the exponential case, in the case of the exponential distribution, the hazard is given by 1 over rho, right? And so we can get an estimate of that by using 1 over the exponential of the coef of our model here, right? And so if I look at it, we get this estimate of 0.0082. That's our estimated hazard here. Of course, because this is just sort of our standard inference, we can get a confidence interval around it. So I can define the confidence interval to be, say, 1 over the exponential, and then the first term of it is going to be the coef of this minus q norm 0.975 times by the standard error of our estimate here, which we can do just as the square root of the model variance. So there's model var here, and this is just going to give us the variance of our intercept term. And so if we take the square root, that gives us our standard error. And then if we go over for the upper bound, it's going to be the same thing except plus. And so if we do this with this transformation here, you can see that we get this confidence interval. So from 0.0086 to 0.0783. And now the one thing to note is that, of course, this is backwards because of the fact that we're doing 1 over. And so the confidence bounds actually should be written in the opposite order. And now we will have a confidence interval that's in order here, right? So from about 0.078 to 0.008586. Okay, so we can use all of the standard types of inference that you would be used to. Now, we also saw in the previous lecture that we had a closed formed version of the maximum likelihood estimator for the hazard in an exponential family. And in particular, what we saw was that the closed form maximum likelihood estimator was the number of total events divided by the total time that was exposed. And so I could define sort of the hazard for the closed form to be the sum of churn event, right? So this is going to count the number of events that we observed divided by the sum of the churn time, right? And if I look at H1 closed form and I look at H1 hat, say, you can see that these are the same estimate, right? So that gives us some a check on ourselves to make sure that what we're doing makes sense, and it seems to. But again, one of the nice parts about doing it through this modeling setting is that we get these confidence intervals fairly easily from there. Okay, so we could also start to try and generate some different plots based on this model fit, right? So what I'm going to do, let's do some plotting here. I'm going to create a times vector here, and I'm just going to make it be a sequence from 0 up to, let's say that we want to do 20 years worth of months, right? That's sort of the maximum that I could imagine someone being a customer at a telecommunications company. And we're just going to make sure that we draw smooth lines, make the length of the output 1,000. Okay, so this is just giving us 1,000 times between 0 and 240. All right. And so if we want to know what the survival probability is, well, we saw that the survivor function of the exponential family is equal to e to the negative t over rho, or equivalently, e to the negative t times by the hazard, because the hazard is 1 over rho, right? And so we could estimate these survival probabilities by giving exponential of negative times by, say, h1 closed form. Why not? They're the exact same value, so we can use that. Right? And so now if I just take a look at the head of survival probability here, you can see that these are estimates for our survival curve. Now, because we have this H1 hat with confidence intervals, we also sort of have this ability to get, say, survival prob lower as the exponential of the estimate on the lower bound. So if I go H1 hat CI1, right? And this is going to give us a lower bound estimate on our survival, sort of doing a 95% confidence interval here. And if I do it with the upper bound, H1 hat CI2, then what we could do is we could plot this survival probability along with the lower and upper bounds, and that's going to give us sort of a sense of what the behavior of this survival function is. So we can do that. I'm going to go plot, and we're going to plot the survival probability based on the times. I'm going to set the type to be line, and I'm also going to set the y limits to be 0 to 1, just so that we get that full scale of the possible outcomes here. And then I'm also going to do lines, and the lines I want to do a serve prob lower by the times, and I'll say set the line type equal to 2, and I'll also do serve prob upper based on the time, set the line type equal to 2 as well. And so make sure I run all of this. Got to get the plot margins there. So there's our survival estimate. You can see it's this nice smooth parametric curve. And we could also add in sort of an upper and a lower bounds. And it appears as though I have the upper and the lower incorrectly mapped, but that's just because of the fact that the hazard is inversely proportional to the values that we care about. But anyways, there we go. That gives us this plot of our survival function. So if we think that the exponential is a good fit to the distribution, well then this is one way that we could get the maximum likelihood estimate. But do we think that that's a good fit, right? And so like one way we could check this is if we go back and we plot the survival object, right? Plot survival object, you can see that it's here. And if I just copy this code down here, we can put it here. And instead of plotting it, we can do the lines on that, and we don't need this. And maybe I'll just put the color to be red so that we can see it nice and easy. But if we now overlay this, so we have our plot, there's our survivor function, and there's our intervals, you can see that, no, it doesn't look like such a great plot, right? We're way above here, we have some okay behavior in the middle, and then we have this chunk down beneath. And so, what are we supposed to do in this situation? Well, one of the things that you could do is to start fitting a more complicated model, which is what we'll actually see in the next sets of lectures. But one other thing that we could do is note that some of this weird behavior is going on because of this big drop off at 1, right? If you imagine that this drop wasn't here and it was sort of smoother the whole way, then, it's probably still not the perfect fit, but it looks to be a much better fit. And so one thing that we could do is we could think about artificially truncating our data, right? Remember, truncation is when you remove people from your sample based on when their event happened. And what I'm suggesting is that we create a truncated model where we truncate at the time being greater than 1. So we throw out anyone who churned before month 1, right? And so what my goal here is to try and suggest, one, how does truncation work? But also, why is it that we might actually care about truncation? So what I'm going to do is I'm going to create a truncated churn data set here, and it's going to be the churn data set, except I'm going to filter down for which of the churn time was greater than 1. Okay, so now we have removed anyone who has their event at time 1. And then essentially what I want to do is create the same model that we have up here. And so I have some code typed out that I'm actually going to copy and paste, then we can go through. But you can see I have this model 1 truncated, which is going to be a Survreg, where we have the same survival object, but now here the data is going to be the truncated churn. Same thing, distribution exponential. And then I'm just estimating the hazard function as 1 over that parameter, and I'm estimating the survival probability as the e to the negative times, which is still just this times sequence up here, timed by that, okay? So if I fit this model, and I fit that survival probability here, now what you could do is we could come back up and do the same sort of plotting here, except instead of the plot of the survival object, we would actually want to do a truncated survival object. So maybe I'll come in here and I'll say truncated, or survival object truncated. It's going to be serve of the truncated churn time, truncated churn event. Oh, serve. Alrighty, and so then we could, instead of plotting the survival object, we just plot the survival object truncated. Instead of the survival probabilities, we do the survival probabilities truncated. So if we plot that, and then we overlay this line, you can see that in this truncated model, it's still not perfect by any means, right? We're still overestimating and then underestimating. But when you compare it to this plot, you see that we're getting a lot closer, right? And so there's still, without using anything else in the model other than just the exponential distribution, you can see that we're sort of getting an okay fit here, right? So that's kind of interesting. It's again not perfect. I would not suggest that this looks to be exactly the correct idea here, but more or less, we're getting a much better fit. So that's sort of this interesting procedure that we can take. Now, the last thing that I kind of want to talk about here is this idea of doing some subgroup analysis and using likelihood ratio tests to see whether those are necessary. So as we saw earlier, there's a ton of different variables. One of the variables, though, is whether or not the customer is paying for phone service. And so you can either have yes or no for phone service, right? And so there's sort of two groups of customers based on whether or not they pay for the phone service. And so we can think about doing a subgroup analysis here. And so what I want to do is say define a model 2 for the phone, and it's going to be the Survreg again. And so we have the serve, it's going to be time, event, no factors to explain it. We're going to say the data, and we'll just work with the truncated data because it seems to be fitting a little bit better. But I want to do a subset here where the phone service is equal to yes, and the distribution is going to be the exponential distribution. Okay, so we fit that on just the subset of the data that have phone service, and then I could do the same thing on just the subset of the data that don't have phone service. So I'll type this all out just to re-emphasize all of the points here. So the data is going to be the truncated churn still. Now, the only thing that we're changing is that instead of the subset being phone service equals yes, we'll say phone service not equal to yes. Get that out of the way there. And then still distribution equals the exponential distribution. Okay, and so what we've done here is we've fit two different models. So if I do summary of M2 phone and summary of M2 no phone, and then can sort of show you the results here, see that for no phone we get this 5.1046 versus 5.0208. And so it seems like maybe there's actually a different parameter whether you've paid for the phone service or you've not paid for the phone service, right? And so you could think about, we could calculate the independent hazard functions for each of these. We could calculate the independent survival probabilities for each of these. And then we could, see, are these fitting better, right? And so you could think about doing sort of the same type of analysis that we were just doing, except within each of the subgroups. But what I want to point out is that actually fitting these two models is a way of fitting a sort of nested model structure. And in particular, these are the larger model, right? So if you think about the likelihood ratio test when you first learned it, the idea is that you can do a constrained likelihood, and if that constrained likelihood appears to fit the data just as nicely, then it works just as well as the unconstrained likelihood. So in theory, what we are saying is we could compare whether we need these two different models to fit the data as well as a single model or not. So if we call this, say, row 1 for the phone model and row 2 for the no phone model, right? We can think about testing the null hypothesis that row 1 is equal to row 2, which is equal to just some other row, and that some other row is the row from this model up here, okay? And so this is sort of a standard likelihood ratio test that we can do, and so we could actually compute the likelihood ratio test statistic. And how would we go about doing that? Well, we could say the likelihood ratio test statistic is -2 times, and then we need to get the difference in the log likelihoods. And so I could go model 1 truncated, log likelihood, and it's actually, if you look at the log likelihood call here, it's going to be a two-dimensional vector. In this case, because it's just an intercept, we can grab either of the terms, so I'm just grabbing the first one. And then from that, you subtract off the log likelihood of the model, the unconstrained model, right? And that's going to end up being the sum of the log likelihood from model 2 plus from model 2 with no phone. So that's going to be subtract off M2 phone log likelihood 1 plus M2 phone log likelihood 2, right? And the reason we get that addition, just to clarify, is because we're thinking about estimating those two parameters. So the likelihood is the product of the two likelihoods, which means that when you take the log, you're going to get the log likelihood of the first one plus the log likelihood of the second one. And we'll set that to be a 1 just to keep things consistent. And so you can see we have this likelihood ratio test statistic is -14,000 something, right? The number of degrees of freedom is equal to the number of constraints, which in this case is actually just 1. And so we can get 1 minus p chi-square of the likelihood ratio test with 1 degree of freedom. You can see that the p-value is greater than 0.05. It's effectively 1, which means that you do not reject the null hypothesis. So actually, I just realized, and I should have realized this when I was looking at the likelihood ratio before, I had a slight typo in my equation up here. So I had the model 1 truncated log likelihood, that was fine, but then I had this as model 2 phone as well. And so if we rerun this likelihood ratio test now, the LRT statistic is now 0.858697. Before it was negative 14,000 or something, and that should have struck me as implausible because the likelihood ratio test statistic is supposed to be positive. Okay, and so now if we compute this p-value, we again still get a p-value that's greater than 0.5, but it's not 1, right? So sorry about that typo, but I caught that there. Now, what I want to point out to you actually is that in this case, there would have been another way of us getting to this same test statistic here. And the reason I want to show you this is to sort of give you a sense of what's to come, right? So if instead of having fit these two different subgroup models, if I had come in here and I had said model 2 is going to be given by the Survreg, and I could do serve time event, and instead of doing just to a 1, if I said that we went to phone service, right? So that's the variable we were grouping on before. And then I do data equals truncated churn, and we do the distribution as the exponential distribution, right? We can fit this model. If we take a look at the summary now, you can see that we get this output summary that looks a lot like the standard regression summary that we're used to. But here, if I had run an ANOVA between model 2 and model 1 truncated, you can see that we get that same p-value, right? It's 0.35. So that's a test. And so in this sense, when we're using the exponential distribution at least, we can view this subgroup analysis as sort of these nested models, right? But the reason that this is nice is because, well, we could just specify a little regression equation here. And through the specification of that regression equation, we can start to fit models that are actually, fairly complicated. And that's what we're going to be doing starting in the next lecture. So we're going to introduce the concept of an accelerated failure time model, and this Survreg function is actually fitting accelerated failure time models. That's what it's doing under the hood. And so while all of this was just us talking about sort of the likelihood fit for exponential distributions, you could have inserted another distribution there as well. As soon as you start including covariates, now we're fitting accelerated failure time models, and they're quite a powerful type of model for continuous time survival data. And so we're going to dive into that conceptually, theoretically, and through an application starting in the next lecture. So again, all of this is posted on the course website. I hope it all made sense. If you have any questions at all, please let me know, and I will see all of you in the next lecture.